continue and hopefully end the Shor Code. So we have been doing this for a while. So this the coding is that the logical qubit is encoded into this these are normalized, and then this one is with the minus signs. These are, by the way, this one is often called only this part, okay? This part is called the GHZ state, Greenberger-Horn-Zeilinger. Sometimes called Greenberger-Horn-Zeilinger-Marmin. Sometimes called the cat state. Many names to it. And it has a lot of utilities in quantum information. And nice to see that this is another. And so we have encoded a single logical qubit into 9 physical qubits in this way, and we have seen that if there is a bit flip or a phase flip in any one of these 9 physical qubits, then it can be detected and corrected. But of course, there are, in general, other types of errors that may happen, as we have discussed before, and we want to see what happens for that. So let us begin with the following. Another type of an error. So suppose now that there is the additional possibility that bit phase flip can occur. Okay, a bit phase flip is you change the bit as well as the flip, as well as the phase. Essentially a sigma y.
On the same bit.
It can be anywhere, but it happens only in one place. So any one of these 9 qubits is either being inflicted by a bit flip or a phase flip or a bit phase flip. This is the situation that we are going to consider. We have already seen that if any one of them had been inflicted by a bit flip or a phase flip, then we can correct them, correct it. So here we are considering that there is this additional thing also happening along with the others. So we will see what happens if this is also there as a possibility in the channel or in the storage device. Yes? So now bit flip or a phase flip or a bit phase flip occurs on at most one of the 9 So just to be specific, suppose that bit phase flip occurs on the first physical cube. Okay? This is what, by a chance, this happens. This is one of the options, yes? Then the encoded state meaning the qubit that we had was this. This is a single physical qubit, and then we had put in 8 auxiliaries, so that the 9 physical qubits is transformed into 0L plus 1L, where this is now a 9 qubit state, yes? Where this one is 3 GHZs with the plus sign, and this one is 3 GHZs with the minus sign, yes? This is the encoded qubit. A bit phase flip has occurred on the first physical qubit. So what you get is an A. Here there was a GHZ, but instead of that, now we have a 1, 0, 0 minus 0, 1, 1 in the first one. Yeah, this was 0, 0, 0 plus 1, 1, 1, but a bit phase flip has occurred here. So it changes the bit and the phase. So it has become this. Yes? This is in the 1 tilde, if you remember this notation. This was 1, 2, 3. And you have a plus, which is in 2 tilde with a tilde. This is this exactly. And a plus tilde on the 3. Plus B. Now, this thing here was this. And now a bit phase flip occurs and you get 1, 0, 0 plus 0, 1, 1. 1 tilde and a minus 2 tilde and a 3 tilde. Yes? Clear? This is what you get out of the channel, assuming that the channel is inflicting a bit flip noise on the first physical key. We are, however, ignorant of whether the error was a bit or a phase or a bit phase flip, and where and of on about and about the qubit, the physical qubit, on which the error was inflicted. Yes? We don't know this. This is by a chance this has happened. Then this occurs, but we ourselves don't know whether this has actually happened. So we have to correct the error without this knowledge. So because we don't know whether this has happened, we go through the same syndrome diagnosis analysis as we did in the previous cases. We do the bit flip syndrome analysis and the phase flip syndrome analysis. And you will see, or you may already see, that this will actually correct this error as well. Go through the same syndrome diagnosis as for bit and phase flips, meaning that the case when the channel was such that either a bit flip or a phase flip would have occurred, may occur in one of the 9 physical qubit, or nothing happens anywhere. So we act with this series, yes? This, you first do the bit flip syndrome analysis, which is sigma Z1, sigma Z2, then sigma Z2, sigma Z3, and so on up to sigma Z8, sigma Z9, yes? And we detect a bit flip at. So if you do the checking, you will see that this bit flip detect this bit flip that has happened in this case if you when you come to this. Call it a bit flip because it was not actually a bit flip, it was a bit phase flip, but we don't know that as yet. Detect the bit in this particular case. In this particular case, and we do not proceed any further, we do not proceed any further in the bit flip syndrome analysis, syndrome diagnosis protocol. But that was because of this particular case. In general, we have to proceed all the way to the end. Up to this. Yeah. After the detection, we correct the bit flip error. And get this thing with this 1 and 0 interchanged, which is just the minus tilde, yes? So you get A minus tilde 1 tilde plus 2 plus 3 and plus B plus tilde minus tilde minus tilde. Yes. But this has to be followed by phase flip syndrome diagnosis, and there that we have done previously anyway. And if this occurs, this can be corrected by the phase flip syndrome diagnosis.
So, in the bit flip, we have four, like those. The POV model has 4 projectors. No, not projectors, but 4 measurements. P1.
4 projectors.
Yeah, higher rank projectors.
This is the higher rank.
So, in the case of only a bit flip, let's say P1 is the one that hits. Oh, so P1 is the one that hits only when nothing happens to no error happens. P2 is when the first bit, P3 is that. But what only in the bit flip case and bit flip plus phase flip case are 2 different projectors hit, right? Or is it the same projector?
It's the same thing. This the bit flip analysis is blind to this sign here. It doesn't look at the sign.
Oh, yeah. It has both the terms.
It's just a projector of this and this, so it doesn't look at the sign. It's an identity in that space. So we now do the phase flip syndrome diagnosis and are able to correct that error also. Yes? So, this seems, well, mathematically it's sort of an easy exercise, but it gives us sort of an interesting twist, if you say, or whatever, to the story, in the sense that until now we have been doing error correction codes where we assume some type of an error is there in the channel, and then we try to write a code that corrects that error. Whereas here we have a code, we started off in the same way, we wanted to correct two types of errors, and as if an accident has happened, and this has corrected another type of error as well. Yes. So we have got protection from a type of error that we did not intend to be protected against.
So even if the bit flip error occurs on some set of qubits and the phase flip occurs in some other set of qubits, it will be able to correct that type of error also.
No. We are not considering those type of errors. So here the error occurs in only one of the qubits.
But had it happened, would it correct this?
We have not analyzed that. Yeah.
Yeah, it will.
No. This is not meant for that. It is meant for a single. It's meant for error in any one of the qubits, and that error is either a bit flip or a phase flip, or it may accidentally correct some other errors as well, but we are not analyzing that. We are analyzing only that the bit flip or the phase flip or the bit phase flip by accident has happened in one of the qubits. And this can be corrected.
So you're saying because maybe bit flip may be registered as phase flip and what is it, the two projectors bit flip?
Yeah. I mean, so this we have not analyzed. This is what I'm saying. We have not got prepared to do that. But I mean, this is a very good thing that we were not analyzing, we were not prepared to have the protection, but we had protection from another type of an error. But that's not the end, right? I mean, there are other types of errors, this we already discussed on the last day, that there are other types of errors that can happen. The question is whether those type of errors are also corrected by this. And so for the impatient, it does. So this is the end of the story in the sense that this 9-qubit code can correct against any error that can happen in one of the qubits. Any error meaning it can be that one of the qubits is completely lost and is replaced by complete noise or anything else. It can be corrected. Any one of the qubits.
With the knowledge of what?
With the knowledge that it happens in only one of the qubits.
We don't even need to know what the error is.
We don't even need to know what the error. It has to be so.
Arbitrary phase.
Yeah, it satisfies quantum mechanics. Yeah. It cannot be an arbitrary noise in the sense that it has to satisfy quantum mechanics. So this is what we will see. So let the psi up to 9, we denote it by this 0L plus D1L, and this has all the 9 ones. Okay, so 1, 2 up to 9, and this is also 1, 2 up to 9. Okay. This is the encoding. This is before the noise acts Okay, this is, so we had a psi of a smaller system, we went to a bigger system, and that is this. We know how to do it, there is a circuit that does that, and we send it through a channel, or we store it in a device. Let now an arbitrary noise act on any one of the 9 physical qubits. Okay. Let us denote this by lambda. Let it act on the ith physical qubit where I is 1 up to 9. So, the output from the communication channel or the storage device after some time is lambda I, putting the superscript I to denote where it occurs. Tensor, this is the identity operator. So put it I bar, not I, identity on everything else, on, and this is 1. This is this projector of this. Yes. This can be expressed as, in the cross decomposition, or there are many names associated to it, Krauss, Kosakowski, Sudarshan, Jamyonkovsky, Choi, many people have done this, done some aspects of this. It can be written as AJ psi AJ dagger summation over the J, where is the identity operator on the ith qubit. Yes, so I have decomposed only this one. So this, there should be a suffix superscript I that I am not writing, and there is a tensor this that I am also not writing. Okay. This one is on I, the ith qubit, whereas this one is on all the 9. So except for the I, there is identity operating on all the rest of the qubits. This is a so-called CPTP map, yes, so completely positive stress preserving map. The arbitrary map that can, that is quantum mechanically allowed. AJ is an arbitrary operator on the ith Hilbert space. It's a two-dimensional complex Hilbert space. And this identity is the identity operator on that Hilbert space. Everybody remembers this decomposition? Now, AJ is an operator on a two-dimensional complex Hilbert space. So I can write this AJ as AJ0, the identity operator on that space, plus AJ1 sigma x plus AJ2 sigma y plus sigma z. Because this Pauli matrices and identity span the space of operators. Okay. And that's the crux. So that this AJ psi that appears there. So remember that there is a I that I am hiding. There is a small I over here that I am hiding, and then there is this tensor this that I am also hiding. Okay. This is AJ0 psi plus AJ1 sigma x psi plus AJ3 sigma z psi again here this is a 9 qubit state. This is acting on the ith physical qubit, ith qubit of that array. Same throughout. We'll take a slight detour. Problem. If rho is a density matrix, which means that it is positive and Hermitian and has trace 1. Yes? On a Hilbert space H, this is Hermitian and positive semi-definite. Operator on H. For any operator A acting on H. that this looks like this. So this is like an arbitrary term in this cross sum. Yes. I judge that you have done this already before. It may not be a density matrix in the sense that it may not be trace 1. It may not be of unit trace, but otherwise it is. Do it explicitly. You take the Hermitian conjugate, you will see it's the same thing. And the positivity, you take an arbitrary vector, you will see that the ket bra with the vector is always positive. So I'm not doing it. The second problem is that the numbers, this also I judge you have done before, the numbers AJ row, AJ dagger, this set, this is the running variable of the set. This forms a probability distribution, yes. If rho is density, H, and this is a valid Krauss sum. Is the identity on this Hilbert space H. With AJ being arbitrary operators on that same Hilbert space. This is essentially the Bond rule, yes? This is the Bond rule. So, rub this off. So, this thing that we wrote before, this, the state after the error, this AJ psi AJ dagger with AJ dagger, AJ as the identity on the ith space. This was the state that came out of the channel, yes? Or the storage device after some time. This was my encoded state, whereas this is the encoded, this is the state that happens to the, what happens to the encoded state after it is inflicted by noise. This can be considered as the average of the quantum ensemble So what is a quantum ensemble? A quantum ensemble is a situation or a source that is preparing the state, quantum state rho j with probability pj. Yes. So you have a situation which is not deterministic. It is preparing states at random, but is not completely random. It is promised that the state that is being prepared is the state rho j, and the probability that rho j is prepared is pj. Yes. So you can think of this state as the average of a quantum ensemble, where this Pj is trace of Aj psi Aj, and rho j is Aj by Aj. This is writing in another, it's the same thing. I mean, it's writing in a different language. So this is the Pj. So the average state is, of course, summation Pj rho j over j, and the Pj cancels with this, and what you are left with this, which is actually this. Yes?
Is it dagger?
Yeah, so thank you. And there's a dagger here as well. Thank you. So we can think of the output from the communication channel as one of the states rho j with certain probabilities. So the state at the output is Aj psi over square root of Pj. Now I'm writing the I to be careful. It's clear? This is the rho j. Rho j is the projector of this. But when rho j is a pure state, I'm writing it as a pure state. I'm ignoring the phase will anyway vanish. So I ignore the PJ as well, it will not be important. This up to normalization for some G. So it will, one of these will appear for some J. Tell me if you don't understand. Sheer magic. If all errors will now be corrected. Maybe you already
One of
understand.
these will appear in the sense.
Pardon?
One of these will appear as in what?
Well, I mean, you don't know which one will happen. So the process is probabilistic. As we have written, we have found out that you deterministically obtain this thing. But it's equivalent to assume that you obtain one of them with some probabilities. You have to normalize it. So deterministically obtaining this is the same as probabilistically obtaining this thing with this probability.
In the statistical sense, yes. But in a single operation, what are we saying?
Yeah, so I am deterministically obtaining this.
So this was my lambda map, the noise map.
After the lambda map, I have got
Yeah.
this.
So this is the decomposition of what lambda does to the state. Now, the state can be arbitrarily shifted by that lambda, one of the qubits. And that is given by this combination.
Exactly. And you deterministically obtained it. We have assumed that it is a trace preserving, completely positive map.
Whatever.
You can handle non-trace preserving things also. We are making things simple by considering only trace preserving maps. So you obtain it deterministically.
Yeah, but this entire error that happened to the qubit is in superposition, like in the sense, this is the combined error.
What do you mean in superposition? It's in a mixture. I have written
Yeah,
as a
it's
mixture.
a mixture of errors. In the sense
It's a
that
mixture of
it's not
errors.
that one of the errors AJ happened and then some AJ plus 1 happened.
No, but this is what I'm saying. This is equivalent. That's the power of the entire thing. I can
Equivalent
think in my mind, if the other thing that you were saying had happened, you would have got the same state.
Yeah.
So you cannot distinguish them. Physically, you cannot distinguish.
Statistically, no. But that requires multiple
No.
iterations, right?
So this is the point. That suppose you are in a situation where sometimes you get this and sometimes you get the other one and you know the probabilities, but you have only one occurrence of that.
Yeah.
You are getting only one occurrence of the entire thing. So
That
you have
was
no
the-
information which has happened, but you know what are the things that may have happened.
So the way you
So the state is just the average of this. This is what you do.
The state is average of this, but you only have one go at this. Like
You only one go. So you have only one copy of the entire thing.
Yeah.
But since you don't have this is the static description of quantum mechanics. If you don't know the thing, you average over the options.
No, but we in order to average
Mhm.
experimentally,
Mhm.
we'll have to send multiple times.
No, this is what I'm saying. It's not I that I am preparing, it's the channel that is preparing for me.
Yeah, but each time.
So I don't prepare it even.
No, but
I am ready for that error. That's the point.
in the statistical sense, you can be. Like, if you decompose it like this is saying that error AJ happens PJ of the times, fraction of the times. But the combination of error AJs are happening, A1, A2, A3. The combination.
But these
is
are the
happening.
same things. This is what I'm saying. At the level of the quantum state. No. What do you mean statistically? At the level of the quantum state of a single instance.
Yeah, but they're equivalent statistically. As in, if you do a bunch of measurements with the same error.
It is equivalent with respect to any dynamics and any measurements that you can do quantum mechanically valid on that system. Because the quantum states are the same. Even at the level of a single copy. That's the crux of the statement. You have just a single copy of the entire thing. I am just thinking it probabilistically. It hasn't happened. But the point is that if that thing, what I am thinking had happened, you would have given me the same state as this. This is the crux of the entire matter.
So what? Okay. let's see what we are doing after this.
After this is nothing, this is the end actually. This is the main thing. I mean, so this is, I mean, of course you see, I mean, the thing has happened already here. You have, these errors we already have corrected. So if this can be only this, then that's it. But we'll see why.
No what?
Okay, so let's not go beyond this. So after I say the next line, you will see why this is obvious. But up to now, this is the main. So first of all, this is the thing that we have got out of the channel. This is an arbitrary noise. We have made no assumption except that it is stress preserving and completely positive. And that is all that you have in quantum mechanics. I mean, there are some other things. Let's not go into them. There is this non-stress preserving map that can be easily put in. There are these non-CP maps as well that can also be handled, but let's not go into that. So let us restrict ourselves to CP-TP maps, stress preserving completely positive maps. And that looks like this, where these edges are arbitrary operators on a qubit Hilbert space. That can always be written like this because the Paulis and the identity span the space. There's no restriction on that. So we have not made any new assumption on the noise. And now what I'm trying to say is that this state, having been obtained deterministically, is equivalent to the average state that you obtain when someone promises to give you, instead of this ensemble. So it's a source that is giving out rho 1 with probability P1, rho 2 with probability P2. This is the promise. The source is promised to be that. And you get only one of them. What is the state that you have? It is this state, summation of Pj rho j. This is nothing quantum about it. We do it in classical mechanics as well. Whatever measurements that you can do on that, whatever dynamics that you can do on that will not change. This change in the thinking will not change anything in the dynamics, nothing in the measurements. This is the statement that I used to make.
Sir? So when you wrote AJI, what is that?
Just from here, I have been ignoring that I all the while. So you remember that the AJ is decomposition of the lambda, and that lambda was acting on the ith qubit. Whereas on the other ones, there was an identity operator. But when I wrote this Krauss sum, I ignored that superscript I all the while. But now I want to be more careful and I have written the I there. So if you wish, you can put all the while the I on top everywhere. And I have also ignored this tensor identity I bar. That also I have ignored. That also is there. Fine. We now do the same syndrome diagnosis as before. That is, we measure sigma z1, sigma Z2, sigma Z2, sigma Z3 up to sigma Z8, sigma Z9, and then we do the face flip syndrome diagnosis. Diagnosis of the syndrome, when the error has been diagnosed, has been detected, collapses the encoded state onto psi or sigma x I psi or sigma y I psi or because you remember that this AJ psi is equal to is A, what was the notation? AJ0 I'm writing the I now. With some probabilities. This happens irrespective of which J we are in. We have pretended that we are in one of them. It is with some probability. That thing is this pure state. This pure state is a sum of them. We have pretended we are in some J, but every J looks like that. And we do that bit flip and face flip syndrome diagnosis. This projects us into one of them and tells us in which qubit the error is and what type of error it is. Is it a bit flip or a face flip? Sorry, this is the bit flip. Sorry, this is the bit flip, this is the face flip, and this is the bit face flip. Know what the error is. can then be corrected by a local unit. I mean, local with respect to a physical qubit. This is Shor Code.
So this part is shown.
Hmm?
This part Shor has shown.
Well, Shor, I don't know the history who showed what, but I guess he did the entire thing. The bit flip code may have been known before. I am not sure about the history. Questions, comments, criticisms? Well, otherwise